12.5, we're going to look at level surfaces, but before we do that, we want to do the level curves. So level curves is another name for contour diagram. So I want to do the contour diagram for z is equal to y squared minus x squared. So what happens with this is that we want f of xy to be equal to c. So I'm going to use different values of c and graph each one of them and then see how they map out. So for instance, this one would be y squared minus x squared is equal to c. And so we can take different values of c and figure out what they look like. So this one's y squared minus x squared is equal to 0. That's just y is equal to plus or minus x. So I'm going to get this drawing here with one value there and one value there. Y equals x and y equals negative x. Now try c is equal to 1. Well, this is what we call a hyperbola. Hyperbola is going to look like either this or this, depending on which value here is positive, which one's negative. Well, since the y is positive, we're going to have this one. Y is the positive version, we get this one, and if x is positive, we're going to get this one. So that just means that these are two opposite signs. So if you can plot a point, you're going to have a point that's going to be 0, 1. That works for that. And then you're going to go and approach these asymptotic lines. And so I'm going to get this curve here too. Okay? Now if I do c is equal to 4, y squared minus x squared is equal to 4. The general form of a hyperbola is x squared over 4. I'm sorry, y squared over 4 minus x squared over 4 is equal to 1. You always set it equal to 1. If we have these two bottom values, 2 squared, this 2 would be your value that you'd go from the 0, 0 point. So if I go out 2, that's the value I'm going to have. So this is going to be my next level curve here. And so on and so on. Now what if c is equal to negative 1? That means that x squared minus y squared is equal to 1. So you see I just changed the signs of everything. So now I'm going to get, and let me put this in a different color, I'm going to get a hyperbola that opens this way. Okay, and then so if I go c is equal to negative 2, I'm going to get x squared minus y squared, oh let's go 4, is equal to 4. And so once again, x squared over 4 minus y squared over 4 is equal to 1. So this is 2 squared, so that means I'm going to go out 2 units this way, and then I'm going to have my hyperbola. Okay? So these would be level curves for our contour diagram for this thing right here. And notice that when I graph these red ones, the red ones, besides y equal to x, whatever, those would be below the, what I want to say, the xy plane, because z would be negative. And then the purple ones would be above the xy plane because c is positive. Okay, so I hope that helps with level curves. What we're going to be doing is adding another dimension, so then we're going to have level surfaces for 12.5. By the way, go ahead and graph this with your 3D grapher, this right here, and then see what it looks like and see if my level curves kind of match up for that. And lastly, I put the c equals 0, c equal 1, c equal 4, c equals 0, c equal negative 1, c equal to negative 4 to give me my height for those respective values. Now we want to deal with representing function of 3 variables using a family of level surfaces. And so we're using 3 dimensions to represent 4 dimensions in some respects. So with this, we have a level surface or a level set of a function of 3 variables, f of x, y, and z, and as a surface form of f of x, y, z is equal to c, where c is a constant. So we're going to take this function, set it equal to a bunch of c values. The function f can be represented by the family of level surfaces obtained by allowing c to vary. So it's exactly the same as what we just did, except for now we're one more dimension. So example number 1, the temperature as we go here is based upon 3 variables, one in the x direction, y direction, z direction. What do the level surfaces of the function look like, and what do they mean in terms of temperature? So when we have this function, we're going to look at this level surface and all these level surfaces. So here's a picture down here of this thing. And so as I take and I have some sort of cold source in the middle here, or however you want to look at it, as we get further away from this, we're going to have different layers. It's like an onion. So inside, it's always one temperature on this inside sphere, and then the next sphere, it's always one temperature when you're that far away from that, so on. And so we can do these level surfaces to give us a representation of what our temperature will be at a certain time. So the solution here, they said, well, okay, let's look at one of these. T is equal to 100. So that's like C is equal to 100. And so we're going to get x squared plus y squared plus z squared is equal to 100 degrees Celsius. And so that means that when I am a radius, this would be r squared, away from that center point, then I'm going to be 100 degrees Celsius there, okay? And so it's going to be a radius of 10. And then what we can do is do other values of c. So they got 200, they got 300, and then we can get all of these different values to see what happens with them. So your picture might not have set up as well as this, but notice that each one of these layers is corresponding with each one of these different C values. We could keep on going on too if we wanted to and just add more layers. But that just means that when we're on that particular sphere, that temperature is going to be exactly that amount of the radius squared. Okay? So that would be what we would call an example of level surfaces that represent our 4 dimensions that we do have. Can we look at a picture of 4 dimensions? No, not really. So this is just what's represented for us so we can play around with what happens at different occurrences. So in summary of this, we have that the level surfaces, they go ahead and represent 4 dimensions using a bunch of 3-dimensional figures. Level lines or contour lines represent 3 dimensions, and what we're using is 2 dimensions to do that. So here now we have a catalog of surfaces, and I purposely messed these up. And what I want you to do is see if you can play around and try to match these. I should have gone through the 2-dimensional figures for an ellipse, the equations for ellipse and a hyperbola, and that might help you, but I want you to try to match these up and see if you can figure out which ones go where. And generally the top ones go with the top figures and the bottom ones go with the bottom figures a little bit, but you can play around with this and see what goes on with that. Then go ahead and graph and play around with the graphs and see which one matches up and what happens for different values of A and B. And then we'll try to summarize the ones that you need to know for sure and then which ones that you just got to have some knowledge about. All right? So once again, it's you playing around with your 3D graphing programs to figure out what these graphs do look like and how you can identify each one. So this summarizes the same thing, is that if you do have something that's in 3 variables, then what you can do is go ahead and represent it with 2 variables but repetitively. And so it can be a member of the family of level surfaces representing the 3-variable function as such. So now if we do this, this is just another example really. We can take this again and then find one member of the family and maybe solve for one of the variables. A lot of times solving for z is quite handy. If we do take this same exact equation that we had before and use one example of a c value, then we can go ahead and solve for z. Notice that we do get the plus and minus here. So what does that mean for us on our graphs? So I've done this one and graphed it for you. This just turns out to be the sphere. So when we do this sphere, if I do graph and solve for z, I'm going to get the positive piece and I'm going to get the negative piece. Well, the positive piece, this is just the same thing as semicircles. In fact, let me do this. And so if I do the purple, that's going to be the positive piece. So if I shade this, it's just going to be this portion here. So that's the top piece, just like in a semicircle. And then let me use a different color. Let me use black. The black is going to shade this bottom piece because it represents the negative portion of that. Now we could do this with other values too, but this is just another way to represent these functions. Go ahead and solve for z, get it in terms of one variable, solve for it, but then you get two situations, so you might get the top and the bottom of the sphere, or different shapes depending upon what it is. Okay, so that's another example that you needed to see. All right, thanks for listening to this, and I hope that you do well with your homework. Let me know if you do have any questions. Thanks, have a great day.